Hello, I am Vasudha and I am from Team 11. I belong to P section and today I'm going to talk about our gaming machine that is Smack the Duck. We are doing this under the guidance of our mentor Professor Sanjeev Kavle. So, as you can see, our problem statement, our problem definition is displayed. And so, according to our need statement, we were asked to make an innovative, interactive robotic game. The client clearly mentioned that she was not very happy with the basic claw machine. As we move on to the next slide, you can see that we have made a function tree. Our main intention to make this was for a better understanding of our game so that we know our subsystems well. In the gaming machine, we had four main subsystems, which were handling the duck, handling the hammer, casing, and interface. Here you can also see that the subsystems are further classified. Firstly, our job in the duck handling unit was to control the duck pop and managing the frequency of pop. Then, in the second subsystem, that is the hammer unit, our task was to control the hammer and sense the hit. Thirdly, in the casing unit, we had to look over at switching the game on and off. Also that we had to display the scores according to the player's game. Then we had to ensure that there were proper sounds made according to our game. Also, the lighting of the game was to be looked over. Finally, in the interface unit, we had to receive input from the gameplay and also calculate scores. So, as to display the game start and also end. As I told you, we basically had four main subsystems identified that were handling the duck, handling the hammer, casing, and interface. As we move on to the next slide, we are going to talk about the generated concepts. We basically had three designs for our gaming machine. The one displayed on the screen is our first design. We had four ducks which were paired. So basically we had two pairs of ducks which were connected to one servo motor each, in such an arrangement that the ducks popped randomly. So as you can see this, this is the placement of the ducks according to this design. Here we are using tiny rubber ducks so that it's easily accessible and the game is efficient. Now let us talk about the hammer. So for the hammer we used thermocol for the outer covering, while at each end of the hammer is a key or a switch. Both the hammers were connected to one servo motor each. We decided to set the angle of the servo motor in such a way that the player could control the hammer and it could hit either of the two ducks in front of it. And as the duck was hit by the hammer, we would get the count of the play. And we also had to display scores accordingly. As you can see, this is our second design. In this design, we came up with something different. In this model, instead of using a typical hammer, we used normal rods which were connected to two servo motors each. The duck pop is same as the previous one. As you can clearly see here, the pop system of the duck, which is taken from a seesaw. Here, instead of doing something with the hammer, we attached a touch sensor on the duck which helped us consider the hammer hit, and here we came up with the concept of using the joystick for controlling the hammer. So here's our third and last design. We are using touch sensors on the rubber hammers which will punch or hit the duck from the top. Here we employed the seesaw technique in both the cases, that is the hammering unit and also the duck popping unit. Here we used buttons to control each hammer. So out of these three concepts, we selected the first design to be the most feasible one. And we will be making our game so as the following design. So now let us move on to our virtual implementation. I will be showing you our 3D model. As you can see, this is our 3D model. These are the two hammers, and as you can see, the hammer moves and there is a switch. As it is being shown, this is how the hammer moves. Also, you can see the seesaw technique, which we'll be using to pop the duck up. Here you can see how the ducks are gonna pop. This is the seesaw technique I was talking about. So, as you saw, that was our 3D model. Moving on to the next slide, we can see this is our circuit diagram, wherein we will be using servo motors, we have breadboard, we have resistors, we have capacitors, we have the Arduino, we have buzzers, and you can see how we have arranged this according to our game. Now, moving on to the next slide, we've got the Simulink model of our game. You can see this is the Simulink model, and I will be showing you our Simulink model in a while.
Hi, my name is Ishwar from Team 11. Team 11, I am about to explain our Simulink model. So we start off with start button. So as long as it is 0, our complete code will not work. So as soon as we set it to 1, our code will start functioning. So the first state we hit here is countdown. So what it does is it will count down from 3 to 1, and it will display that countdown in this window. So it takes one input button, it will produces a output start, which is constantly fed to initialize state. So in this state, so we will stay in this state as long as button is not equal to 1. So when we see that button is 1, we enter this state, and if we observe here is a loop, and each loop will last for 1 second, and each time we loop through, we decrement start by 1. So and we will loop through until we hit start equal to 0. So as soon as we hit start equal to 0, we will enter this state. So as soon as we see that start is 0, we will enter this state from this state, and we turn on buzzer 2 equal to 1, and we will keep buzzer on for 1 second. After that, we will enter into this state, and we will set begin equal to 1, which is an output data, and that begin is shared among 4 units, 1, 2, 3, 4. That begin is shared among 4 units, and another output is buzzer 2, which is fed to buzzering unit, which will buzz for 1 second. Every time it receives a signal, it will buzz for 1 second. So now let's take a look into random angle generator unit. So it takes two inputs, begin and stop. Begin will initialize this system, this unit, and stop will stop this unit, and it will generate our random angles. So we start here with the empty state. We need empty state to put this condition, and once we see that begin is 1, we enter this state, and I'll initialize R variable to 1, and angle, a matrix 1 cross 3 has 3 angles, 10, 45, 80. The angles 10 and 80 are angles at which ducts will pop, and the 45 at which ducts will pop in. So once we're done initializing, we will enter to this state without any conditions, and we'll pick a random integer between 1 and 3, and that will be assigned to R. After assigning R, we enter this state, and we will pick a random angle through R, and we will output that angle for 1.5 seconds, so that we are waiting for 1.5 seconds to make sure that our servo will swing to its desired angle. So after that, once we have swung our hammer, we have to swing it back. So that will be done by duct swings. As I said, 45 angle is angle at which ducts will pop in. So we will stay in this state for 1.5 seconds to make sure that again our servo will do its job. After that, we again get back to where we started. So this cycle is repeated. So this is how our random angle generator works. So let's take a look into joystick handling unit. So this takes three inputs, begin to initialize this unit. VRX1 and VRX2 are joystick inputs. These values varies from 0 to 1023, and this unit, what it does is it will map those analog signals to appropriate or suitable angles, so to hammer ducts. So it produces stop, joy angle 1, joy angle 2, and if we take a look into it, so we start off with setting time equal to 60 and stop equal to 0. As soon as we see that begin is 1, we enter this state. So this state will map our analog signals to appropriate angle. So these both will, after reading analog signals from joystick, and once we are done reading, we will enter this state. In this state, we check for time. Once we run out of time, we produce a stop signal we will set stop signal to 1, which will stop other units from working. And if you observe here, we have two paths from this state. So we choose this path if there is no right or left swing. If there is no left, or if there is a left or right swing, then we will choose this path, and we will wait for 1.5 seconds to make sure that our hammer has swung properly. And after once we swung our hammer, we have to swing it back to where it started from. So that will be done by swing back function. Again, we will wait for 1.5 seconds. After doing that, we will go back and we start from where we left. So it will check for new signals now. So that stop signal is shared among three units, 1, 2, 3. So once we run out of time, this unit will produce a stop signal, so that to stop these all units from working. So if we take a look into circuit completion unit, so it takes 4 inputs: stop, begin, circuit 1, circuit 2. Stop is to stop this working, begin is to initialize this unit, and circuit 1, circuit 2 are the circuit completion signals, and it produces a score as output. It will calculate from score from circuit completions. It will simultaneously it will give a signal to buzzering unit. If you take a look into it, we start with a and state flow buzzer, and we set buzzer equal to 0 and score equal to 0. As soon as begin equals to 1, we enter this state. We will check for circuit completion in both these states, and if there is circuit completion, then we will increment score. Then we will increment score and set buzzer equal to 1. After reading, after calculating scores and all, we enter in this state. So if there is no detection, then we will go back to from where we started to check for next detection. Otherwise, we will wait for 1 second so that we avoid duplicate detections, and we will set buzzer equal to 1. After 1 second, we will check for next detection. And last one we are left with is buzzering unit. So it is very simple. So if either buzzer 1 or buzzer 2 is true, then we will buzz, and we will wait in this state for 1 second. Once we are done with 1 second, we will go again we will check for buzzer 1 or buzzer 2 for true, and this is how it works. Thank you.
So, as you saw, this was our Simulink model. Moving on to the next slide, we have the bill of materials. This includes all the items that we require for our gaming machine. As you can see, we have the breadboard, the Arduino, resistor, LED display, and many more. Yeah, so as you can see, this is the bill of materials of our gaming machine. Moving on to the next slide, we have the motor sizing of the entire system. As you can see, this is the picture of our calculations. Like, we have taken a picture of this, and we will be explaining this to you in a while.
Hi, it's Ishwar from Team 11. I am about to explain our motor sizing. So let me get started from this diagram. So let me explain what this diagram is referring to. So this diagram is referring to this model, not exactly. So if this arm AB is referring to this gray arm, and this mass is referring to the masses of all whatever we have, like duck, this screw, L clamp, and this small arm, it will all add up to mass m. That mass be m. So we can easily guess what r is. So now the equation for torque of this arrangement turns out to be Rmg sine of pi by 2 plus theta. So here r is OA, and force here is mg, and theta is pi by 2 plus theta. So in order to calculate maximum mass or load that can be hung at point A, we can do that by pushing our servo to its maximum capacity, and our servo will experience maximum load at theta equal to 0 degree. So assuming that a torque is maximum and theta is 0 degree, so we need to calculate what m is now. So we simplifying this equation for m, we end up with this equation, and substituting theta equal to 0 degree, we end up with this equation. So maximum load equation is m equal to tau by rg. Now from data we have, and converting those all data to CGS unit, so this is what happens. R becomes 6.9075 centimeter. Torque becomes 18 Newton per centimeter, which will be converted to CGS unit, which turns out to be 18 lakh times per centimeter, and acceleration due to gravity turns out to be 1000 centimeter per second square. Substituting all those data into this equation, we end up to 60 grams of load, maximum load that can be handled by our servo. So we don't think that our load will exceed more than 50 grams, including all those duck nuts, base, uh, and what we have here, like this nut base, this gray arm, and the elk clamp. We don't think that it will exceed more than 50 grams. And since we have ignored friction, and since we are left with 200 grams that can be handled more, so I think that our server will overcome that friction and will function perfectly. And about battery sizing, since we are not using any kind of batteries in our model, we are using two adapters, which has each has a rating of 12 volt and 2 amperes, which which we think that which will be sufficient for our project. Thank you.
As you saw, that was the motor sizing of our system. Moving on to the next slide, we have functional specification of our gaming machine. So the function was to direct the hammer. The hammer will be swinging with any of the angles, that is 10 degree, 55 degree or 100 degree, to attempt to hit a duck. Hammer function, this unit handles incoming analog signals from joystick and map those signals to appropriate angles, which will be processed by popping unit to swing hammers to an appropriate angle. Duck pop. The ducks will pop up once we program popping unit through Simulink model, wherein the duck pops up randomly with the angles 55 degree to 125 degree. Hammer detector. Once the hammer hits the duck, the hammering will be detected with the help of limit switch. LED lights blink for 2 seconds whenever the game starts and ends, along with showing the hammering and scoring. Buzzer. We will be using a buzzer for getting sounds accordingly. To make the game interesting, for different indications, the buzzer will last for 2 to 5 seconds. Scoring. The scores will be calculated and the scores will increase by 1 as the hammer hits the duck. Hammer weight. Reducing the weight of the hammer as much as possible so that we could use a low torque servo motor, and also the hammer gets easier to handle. The duck. Making it accessible and easy to use, we have been using tiny rubber ducks for better usage and increase the efficiency of the game. 4 ducks are being used. Starting the game. The game starts as we switch on our program with a countdown of 3 seconds. Display score. Displaying the score on the screen that we will be using. The scores will be displayed throughout the game and also in the end of the game. Casing. Trying to minimize the weight of the entire game as it must be easy to handle, thus using lightweighted materials along with L clamps for support. Cost reduction. Reducing the cost as much as possible for an efficient and accessible game. Thank you.